In 2015, citizen scientists staring at data from NASA's Kepler Space Telescope noticed something that shouldn't exist. A star, 1,470 light-years away in the constellation Cygnus, was flickering. Not like a variable star, which pulses predictably. Not like a planet crossing its face, which dims the light by a fraction of a percent at regular intervals. This star was dimming by up to 22%, randomly, for days or weeks at a time, and then it would return to normal, as if nothing had happened. Astronomers had monitored over 150,000 stars with Kepler. None behaved like this, not one. The star was designated KIC 8,462,852 inches, the Kepler catalog. But the world would come to know it by a different name, Tabby star, after astronomer Tabitha Boyajian, who led the investigation into what was happening. And what scientists discovered, or rather, what they still cannot fully explain, is a mystery that challenges everything we understand about how stars work. The discovery that changed everything. The Kepler Space Telescope watched stars, waiting for them to dim slightly as planets pass in front. When a Jupiter-sized planet transits its star, it blocks about 1% of the starlight at predictable intervals. But citizen scientists working on the Planet Hunters project flagged KIC 8462852 as bizarre. The star would be stable for months, then suddenly dim by 15%, or 20%, or 22%. The deepest dip ever recorded lasted several days before the star returned to its previous brightness. To put this in perspective, blocking 22% of a star's light would require an object far larger than Jupiter. In fact, it would require something nearly half the diameter of the star itself. But whatever was blocking the light wasn't regular. Sometimes months would pass with nothing. Then multiple dips would occur in succession. The pattern, if it could even be called a pattern, made no sense. Tabitha Boyajian, then at Yale University, gathered a team to analyze the data. They examined every possible natural explanation. Could it be instrumental error? No other telescopes confirmed the observations. Could it be star spots? No, the star was too stable otherwise. Could it be a planet with rings? No, that would produce regular, predictable transits. One by one, conventional explanations failed, and then someone proposed something unconventional. What if this wasn't a natural phenomenon at all? The megastructure hypothesis. In 1960, physicist Freeman Dyson proposed a thought experiment. An advanced civilization would eventually need more energy than their planet could provide. The logical solution: build a structure around their star to harvest its light directly, a Dyson sphere. Such a structure would be massive, blocking a significant portion of starlight. And as it was being built, the blocked light would change irregularly. In 2015, astronomer Jason Wright from Penn State University noted that Tabby's star's behavior was consistent with what you might expect if someone were constructing a Dyson swarm around it. The media ran with the story. Headlines worldwide proclaimed the possible discovery of an alien megastructure. The star was dubbed the Alien Megastructure Star, and What the Fuck Star, which officially stood for Where's the Flux, but carried an obvious double meaning. SETI, the search for extraterrestrial intelligence, aimed radio telescopes at the star, listening for artificial signals. They found nothing. But the absence of radio signals didn't resolve the central mystery. Something was blocking nearly a quarter of the star's light at random intervals, and it wasn't behaving like anything astronomers had seen before. Then archival research revealed something even stranger: the century-long dimming. Astronomer Bradley Schaefer at Louisiana State University examined photographic plates dating back to 1890. The results were stunning. Between 1890 and 1989, the star had faded by approximately 14%. Normal stars don't change brightness by 14% in a century. A 14% decrease over a human lifetime is astronomically fast. This added a new dimension to the mystery. Not only was something intermittently blocking large amounts of light, but something was also causing long-term, progressive dimming. Any explanation would need to account for both behaviors simultaneously, and that's where things became truly challenging. Ruling out the impossible. In May 2017, something remarkable happened. After Boyajian launched a successful crowdfunding campaign raising over $100,000, a global network of telescopes began monitoring Tabby's star continuously. And then, for the first time since Kepler stopped observing it, the star dimmed. This was the opportunity scientists had been waiting for. Not archival data, not a single telescope's observation, but real-time measurements across multiple wavelengths of light, from ultraviolet to infrared. The results were definitive, and they ruled out the megastructure hypothesis. When telescopes observed the dimming event in different colors of light, they found something crucial. The star dimmed more in blue and ultraviolet light than in red and infrared, the signature of dust. An artificial megastructure would block all wavelengths equally. The alien megastructure theory was dead. But here's what they didn't solve. Where was the dust coming from? Why was it behaving so irregularly? And what was causing the century-long dimming trend? The mystery was far from over. The orphaned moon hypothesis. In 2019, astrophysicists Brian Metzger, Miguel Martinez, and Nicholas Stone from Columbia University proposed a new explanation, and it was as violent as it was elegant. Imagine an exoplanet with moons orbiting a distant star. Something catastrophic happens. Gravitational interactions push the planet too close to its star. Tidal forces rip the planet apart. It's destroyed, consumed by its star. But the Columbia team's simulations showed that about 10% of the time, the planet's moons survive. These orphaned exomoons, stripped from their destroyed parent planet, end up in their own eccentric orbits around the star. And this is where the story becomes relevant to Tabby's star. The exomoon, now orbiting much closer to the star, is bombarded by intense stellar radiation. The radiation evaporates its surface layers of ice, frozen gases, organic compounds. The moon behaves like a giant comet, shedding material continuously. This creates an irregular disk around the star, clumpy, chaotic, with material orbiting at different distances and angles. As these clumps pass between Earth and the star, they block varying amounts of light. And as the exomoon continues to evaporate over millions of years, material steadily accumulates in the disk, causing the long-term dimming observed in archival data. For the first time, a single explanation accounted for both the random short-term dips and the century-long dimming trend. Miguel Martinez, lead author of the study, noted that this scenario naturally results in orphaned exomoons ending up on orbits with precisely the properties previous research had shown were needed to explain the dimming of Tabby's star. But here's the truly intriguing part. If this explanation is correct, it means we're witnessing a rare cosmic event, an exomoon in its final million years of existence, slowly disintegrating as it's consumed by stellar radiation. We just happen to be looking at the right star at the right time. What we still don't know. Despite years of observation and dozens of scientific papers, Tabby's star remains incompletely explained. The orphaned exomoon hypothesis is compelling, but it's not conclusive. Some aspects of the light curve don't perfectly match the predictions. The timing between dips sometimes suggests periodicities that don't align with a single orbiting body. There's also the possibility that multiple phenomena are occurring simultaneously. Perhaps there's an exomoon shedding debris, but also interstellar dust passing between us and the star. Or perhaps internal changes within the star itself contribute to the variability. In 2018, researchers identified a possible 1,574-day periodicity in some of the dimming events. That would suggest something orbiting the star on a predictable cycle. But other dips don't fit this pattern at all. And then there's the red dwarf companion. In 2021, astronomers confirmed that Tabby's star has a binary partner, a dim red dwarf star orbiting about 880 astronomical units away, roughly 30 times the distance between Neptune and our Sunday. Could this companion influence the system? Could gravitational interactions between the two stars perturb orbits and create the conditions for exomoon capture or comet swarms? We don't know yet. What we do know is this: KK8462852 continues to be monitored. Amateur astronomers and professional observatories around the world track its brightness. Every new dip provides data. Every brightening event offers clues. Tabitha Boyajian herself remains cautiously optimistic. In interviews, she acknowledges that while the dust hypothesis seems solid, the complete picture remains elusive. The fact that Boyajian's star is rare, she's noted, suggests that the correct solution is an inherently unlikely one. And therein lies the deeper mystery. Why this matters? Tabby's star matters not because it might be aliens, it almost certainly isn't. It matters because it represents something unexpected in a universe we thought we understood. We've become very good at understanding stars as statistical objects, one among billions, each following predictable rules. And then we find one that doesn't fit, one that forces us to consider possibilities we hadn't imagined. The orphaned exomoon hypothesis, if confirmed, would be the first indirect detection of an exomoon. We've discovered thousands of exoplanets, but never definitively proven that planets beyond our solar system have moons. Every mystery solved reveals new questions. Why is this star the only one like it among the million Kepler observed? Are there others we've missed? In 2019, astronomers identified 21 other stars showing similar dimming patterns. Perhaps this phenomenon isn't as rare as we thought. Or perhaps Tabby's star is truly unique, a one-in-a-million cosmic accident, the star that keeps giving. Today, Tabby's star remains under observation. The mystery hasn't been solved, it's been refined. We know it's not aliens. We're fairly confident it's dust. We have plausible mechanisms for how that dust could behave irregularly. But the complete story, with all pieces fitting perfectly together, still eludes us. And perhaps that's exactly as it should be. Science advances not by answering every question, but by asking better ones. Tabby's star forced astronomers to think creatively, to consider scenarios no one had proposed before, to build new observation campaigns and crowdfund research. It reminded us that the universe doesn't owe us easy answers, that anomalies exist, that even in an age of powerful telescopes and sophisticated computer models, nature can surprise us. Somewhere out there, 1,470 light-years away, a star continues its strange behavior. It dims, it brightens, it slowly fades, and we watch, measure, and wonder what we're really seeing. Because nothing about Tabby's star is normal. And that's exactly what makes it extraordinary.